This is problem 82 from chapter 14. Problem 82 reads, if the mass of the Earth is m(e), show that the gravitational potential energy of a body of mass little m located at distance r from the center of the Earth is negative g capital M little m over r. Recall that the gravitational force acting between the Earth and the body is given by capital G times capital M times little m over r squared. This is equation 13.1. For the calculation, locate the datum at r is at infinity. Also prove that F is a conservative force. So first we want to show that the gravitational potential energy is given by what we have here. And to do this, we have given to us capital M, this is the mass of the Earth, and we are looking for the gravitational potential energy at location little r. And they tell us that the force of gravity is equal to, well, the magnitude is equal to what we have here. And we want to find the gravitational potential energy. We can do this by recalling from our equation sheet that the work done is equal to the integral of F dotted with dr. And also, as we saw before, the work is equal to the negative change in gravitational potential energy. So we have the force dotted with dr. Okay, so the force of gravity, we're given the magnitude, but the force would be acting in towards the center of the Earth. The radial direction is pointing, away from the center of the Earth, and so the force is in, the radial direction is out, so we get something negative for our dot product here. So this is negative g m over r squared dr. This should remind you very much of the integrals that you saw in Physics 261. We saw before that the force of gravity, the equation for this is very similar in form to the equation for the electric force. And you can do something similar with the electric force to find the electric potential energy, which you should have done in Physics 261. We are locating the datum very far away at infinity. Our initial point is infinity, our final point is r, and at r is equal to infinity, the potential is equal to, when r is equal to infinity, the potential is equal to 0. So I can do this integral, pull out the masses in G. We've done this integral many times before. This is r to the negative 2, raise the power, the new power is negative 1, and divide by the new power, which is negative 1, which makes this whole thing positive. So we have G E M over r. Now it's positive. We're going from infinity to r, starting at infinity, ending at r. When you put in the upper limit of integration, you get what we had before. When you put in the lower limit of integration, you get 0. And this is u. And we know that the change in potential is equal to negative u. Change in potential is v final minus v initial. That's equal to negative u. G-M-E-M over r. And the initial was 0. We started at infinity, so v final, or v at r, is equal to negative g over r, which is what we were supposed to show. It is negative because it's bound which means if your mass is here at a distance r away from the center of the Earth, you have to add energy to move it away from Earth. You could do this with positive and negative charges too. Just replace this force by the electric force. If you have a positive charge and you have a negative charge nearby, you'd have to add energy to the negative charge to move it away. So this would be a bound system, and you should get negative potential in this case. For an unbound system, if you had a positive charge and a positive charge, they naturally want to go away from each other. And so the potential that you have in this situation should be positive. Okay, so that was only part of the problem. We had to show what the potential was. And we also are supposed to prove that F is a conservative force. To do this, we have to go back to page 216. You should be reading through this on your own, but on page 216, they tell us that to prove that W is conservative, it is necessary to show that it satisfies either equation 1418 or 1419. This is 1418, this is 1419. If your force is the negative gradient of the potential, then it is a conservative force. This gives us one way of checking to see whether or not we can come up with a potential for a force. So if it's conservative, then your force can be written as the negative gradient of your potential. And so we're going to use this to show that our force is conservative. So we have the potential. And so we want to show that if we take the negative gradient of our potential is negative g over r, that we should get the force back. Now, I don't think they give this to you in your book, but this is an operator. We can write this operator in rectangular coordinates or cylindrical coordinates or spherical coordinates. Usually you look this up somewhere. If you're going to write it in rectangular coordinates, it's very easy. This is an operator. It has to operate on something. In this case, it's operating on the potential that we have here. It would be the partial derivative of what it's operating on with respect to x in the I hat direction. It's not taking the derivative of I hat, it's operating on something, and this gives you the x component plus the partial with respect to y in the j hat direction plus the partial with respect to z in the k hat direction. But we don't want to do that in this case because we have a r here. So instead, we can use spherical coordinates. For spherical coordinates, we have, and again, this is not in your book, but you can look it up. So you have 1 over r d theta in the y direction. Okay, now this is del in spherical coordinates. You're taking the partial with respect to theta and phi for these terms here, but the only variable that you have here is r. So when we do this, it's really just going to be, if I take this, write it down here, the negative gradient of what I have here, it's only going to be this term, which is non-zero. So that's going to be, I have a negative sign here and a negative sign here. So how about I call that positive? Then it's dr of what I'm operating on, which is my potential in the r hat direction. And so now I take the partial derivative of this. The partial derivative of r would be, we have the constant here, 1 over r, that would be giving me negative 1 over r squared. To show that this is conservative, when I take the negative gradient of v, I have to get my force back. This is equal to my force And so this is conservative. Okay, so that's all that we have to do for this. And you don't need to remember this. You can look that up somewhere if you need it. They talk about this on page 216. If you're going to do this, you'd probably be doing it in rectangular coordinates. So that's on page 216, and that concludes problem 82.